Okay. Hello, everyone. Welcome to ASA's Statistical Learning and Data Science February webinar. Our speaker today is Professor Mladen Kolar from Department of Data Sciences and Operations, Marshall School of Business at University of South California. Mladen got his PhD in machine learning from Carnegie Mellon in 2013. Despite his young age, he's a prolific researcher and has published over 80 papers on top journals, like 8 great papers a year. His research focuses on high-dimensional statistical methods, probabilistic graphical model, and scalable optimization methods. He currently serves as an associate editor of the Journal of Machine Learning Research, the Annals of Statistics, JCGS, and the New England Journal of Statistics in Data Science. And today, Mladen is going to talk about adaptive stochastic optimization with constraints. And let's welcome Mladen.
Okay, thank you, Juha. So today I'll tell you about something I got excited during the pandemic and been working on this for the last 2 or 3 years. This would not be possible without my collaborators, and specifically my previous student, Senna, who has been a co-author on all of these papers that I'm going to tell you about. So he was really like a lead on many of these works. And I also have 2 previous master students, Yuchen Tang, who is now at Berkeley, and Ilge Hong is a PhD student at Georgia Tech. And then my senior co-authors, Mihai Anitescu and Michael Mahoney. Okay, so big picture problem that I want to discuss in today's talk is how can we handle stochastic nonlinear optimization problems where we have deterministic constraints. So broadly, what we want to solve is this problem where we have a stochastic function, which is the objective. And so what is kind of characteristic in this setting is that we cannot access this function f of x directly, but rather we have access to some sample psi I from some unknown distribution p, and we get realizations of this function at these data points psi I. And so based on these IID samples, we can estimate the function value, and we can estimate its derivative or Hessian, depending on which algorithm we're going to use to find a stationary point of this problem. And then another thing that we have, in addition to stochastic objective, is we have deterministic constraints. We have equality constraints and inequality constraints. And throughout the talk, I'll mostly focus on problems where, algorithms and how to design adaptive algorithms for problems with equality constraints. And I'll briefly mention towards the end how we can handle the inequality constraints if there is time. Okay, so now before I tell you, how to solve such problems, what I want to kind of remind you is why do we actually want to solve these problems? Like, so if I can solve this, who cares? Why should you listen to me? So one kind of prototypical problem that we all try to solve in statistics and machine learning is a problem where we have a finite sum objective. So typically we have some loss function. This could be our log likelihood. It could be a least square loss, where we have some parameter x. This is a parameter of the model, let's say coefficients of a linear regression, and psi I are data points, like for example input output pairs. And finding x that maximizes the log likelihood or minimizes the negative log likelihood is something that we always do. And the way this fits into our stochastic framework is that we can think of having a uniform distribution over the n samples that we get to see. Okay, so here the stochasticity comes into play because in modern data sets we have large amount of samples, and we cannot really evaluate this function f of x in each iteration of our algorithm. So we use some kind of stochastic approximation that we can cheaply compute. And so this is kind of how it relates to the problem formulation in the previous slide. Now, where do constraints come into play? Well, constrained maximum likelihood optimization is something that people have studied for a really long time, over 50 years. And here are just some references, more recent references that point out like what are the statistical properties of a constrained maximum likelihood estimator. And typically these constraints, the reason we have them is so that we can encode some prior knowledge about the model parameters. For example, we could say that coefficient in a linear regression should lie in some low-dimensional subspace. Okay, or for example, our coefficients should be all positive, so we can have constraints of that nature that encode some prior knowledge about the problem. There are many kind of like examples that are more recent. For instance, there are 2 JASA papers in the last 5 years focusing on lasso where we have constraints. So there's this paper in 2018 that looks at the lasso formulation of the problem. So we minimize the residual sum of squares plus L1 penalty on the coefficients. And in addition, so this would be the usual lasso problem, but then in addition, we have the constraint that AX should be less than or equal to B. And then work from Garrett James and the co-authors in, well, this is a paper that was on arXiv in 2012, but it was published in JASA in 2020. They look at general loss function f of x. And again, we have a L1 penalty and these constraints x is less than or equal to b. And so why we care about this is because we can solve problems like portfolio estimation. We can talk about monotone curve estimation, where the constraints estimate, encode the monotonicity constraint. And in general, we can have more general constraints on the coefficients in our lasso, leading to a generalized lasso type problems. So these are some applications in statistical machine learning. A lot of people think about deep learning these days, and also people have looked into problems of constrained deep learning. And so again, like the reason why we would want to put constraints on the parameters in the neural network is so that we can improve the generalization performance of a neural network. Or for instance, we could encode some prior knowledge, for example, from a physical system. We can encode the input-output relationship of a neural network. And another thing is related to robustness. So for instance, if I'm training a neural network model, I would like that map to be, let's say, Lipschitz with Lipschitz constant 1, so that perturbations in the input, let's say, image, do not change the classification of the image if I perturb it a little bit, resulting in a robust network. And so one way to achieve this robustness to input perturbation is to train a model that has orthonormal layers. So in that way, the Lipschitz constant of a neural network would be bounded by 1, leading to this desired property of robustness. Another kind of class of problems is related to machine learning with physics constraints. So for example, physically informed neural networks, where again, we have a neural network that tries to map input to outputs in the observed data. But then in addition, we have some physics constraints come from the domain knowledge that tell us how the model should extrapolate beyond the observations that we get to see. Okay, and then there are many other application domains that are maybe not in the domain of statistical machine learning. For example, the optimal control, nonlinear dynamic programming, problems where we have PDs as constraints to optimization problems, as well as problems in, for example, safe reinforcement learning, as well as putting fairness constraints can be casted as a optimization problem with constraints. So this is why we should potentially care about solving these class of problems. Okay, so now before I tell you how we should go about solving these constraint optimization problems, let me remind you what actually we do in unconstrained optimization. So Zhihua told me that this should be accessible to also graduate students. So I want to review a little bit about what we teach in kind of optimization class 101. So a prototypical kind of class of algorithms that we use to minimize some smooth function f of x over the whole domain where we don't have constraints is a gradient descent algorithm. So this is a very nice algorithm where we start somewhere, just pick some point x0, and then we repeat the following iteration. We move our iterate in the direction of the negative gradient by some amount alpha times gradient f of x. And then at some point we stop. So in this case, this parameter alpha is very important. Like the convergence of this algorithm will depend on how we choose alpha. And also we need to be maybe mindful of how we decide when to stop. But the idea behind gradient descent, oh dear, the idea behind gradient descent is that we don't know how this function f of x looks globally. So we cannot kind of determine where the minimizer or the stationary point is. The only thing we can do is we can construct a local approximation of our function. It's going to be a quadratic local approximation, and then we can minimize this quadratic approximation. So, we don't know how the function globally looks like, but what we can do is we can come up with this green curve that approximates f of x locally, and we can minimize that. Here, the quantity L is an upper bound on the Lipschitz constant of the gradient. Then, if we choose our step size alpha parameter appropriately, so that it's less than 2 over the Lipschitz constant, then what we are going to do is we'll converge to a stationary point of this function f. Again, the proof is so simple. We can simply put it on one slide, and then moving things around, we can achieve this result. Okay, and so here it's important to notice that we don't have any properties about the function f beyond that it's a smooth function. Okay, so the question is then, how do we choose actually the gradient, the step size in practice? So if the step size we see here, it's crucial that the step size is small enough so that we can guarantee convergence. But depending on how we choose it, the performance of the algorithm might be very different. So for instance, if we choose the step size to be too big, we might not converge. If the step size is too small, then the convergence will eventually happen, but it's too slow in practice. And then for optimally, let's say, chosen step size, we get desired convergence. So the problem here is that for any given problem, we don't know what the step size should be. And as a result, we need some kind of problem-specific algorithm to choose this step size. And in deterministic setting, backtracking line search is one such procedure which adaptively can that adaptively chooses the step size. It has like inner loop and allows us to converge to this, let's say, stationary point. Okay.
Dr. Kolar, there is a question from the audience.
Okay, so does it mean could be infinity? So good question. I think this should be bounded. It should converge. So I think this is a typo. This should be something that converges. But thank you for the clarification question. Okay. So what about the stochastic gradient descent? So when we don't have ability to evaluate this function f of x exactly, but we have stochastic access to this function, well, the same algorithm or similar algorithm will work. It's called stochastic gradient descent, where we move the parameter estimate in the direction of the negative gradient. But here, the GK is an estimator of the gradient. Like let's say it's an unbiased estimator of the gradient, and for a suitable choice of step size sequence alpha k, we can converge again to a stationary point. Okay, so the only thing that is different from gradient descent is that instead of evaluating the whole gradient, here we have access to an unbiased gradient. And this notation EK denotes an expectation conditional on being at xk. So we take randomness up to xk, like however we get to xk, we condition on that and just look at the randomness in evaluating the gradient at this point. Okay, so what can we say about this? This is in general not a descent method. So in each iteration, we can potentially increase the function value, the loss value, but in expectation, it is a descent method. And so then we have the following result that is well known. So first, we assume that the variance of the gradient is bounded, let's say by m. Then we have two situations. If the step size parameter is fixed as 1 over L, then our KKT residual in expectation is going to be bounded by some radius of size. It is going to be within a ball of radius of size m, m being the variance of this gradient. And if the step size decays to 0, we have a convergence to a stationary point in expectation. And so roughly we have the two settings. If the step size is bounded by a constant, we'll converge to a neighborhood of a stationary point, and then we will oscillate there. And if we decay the step size, we will eventually converge to the stationary point. But only recently there was a paper from Corgi Paquet and Katja Scheinberg that shows us how we can adaptively choose the step size parameter. Okay, so we don't have to necessarily pre-specify it, but we can probably converge to a stationary point of an unconstrained problem when the step size is chosen in a problem-specific way. Okay, now what happens when we move to constraints? So what I would like to do is I would like to have somehow similar results to what we can prove for stochastic gradient descent, but now with problems where we have constraints. So I would like also to develop algorithms that are adaptive so that the engineer at Google or Meta does not need to spend a lot of time fine-tuning their step sizes, but can rely on the algorithm choosing that optimally. Not necessarily optimally, but in problem specific. So through the rest of the talk, I'll mostly focus on these problems where we have equality constraints. And I'll tell you two approaches of how we can develop adaptive stochastic procedures based on sequential quadratic programming. So first, I'll tell you about the line search procedure, and then later I'll tell you about trust region method for solving these type of problems. Okay, so of course, we are not the first people to consider stochastic problems with constraints. In the literature, like in machine learning literature, people develop penalty-based methods where essentially you construct a penalty related to your constraint, and you add that penalty into your objective, resulting in an unconstrained problem. Now, the problem there is that when you include a penalty in the objective, you need to add some kind of penalty term that typically needs to go to infinity in order for your algorithm to reach the stationary point of the original constraint problem. So solving unconstrained problem then becomes the condition number of that problem becomes very big, and iterations are slow to converge. So these are the drawbacks of somehow penalty-based methods. And another class of algorithms that exist in the literature are projected stochastic methods, where in each iteration one considers projecting onto the null space of this constraint. And this is all nice and good when we can project onto the null space, but not in every problem can we do so. So I will kind of work under the assumption that projection on the null space is not available or it's expensive to compute. And in that case, we need different kinds of methods. So there are kind of recent interest in these types of problems. The most closely worked to what I'm going to talk about was developed by Albert Berhas, who is now at University of Michigan, and his collaborators. So we will kind of extend this approach, which is considered in a fully stochastic setting. We'll develop a line search method that works in a random model setting, and I'll explain that later. And then there's also relatively recent work on stochastic optimization without constraints, where both a line search method and trust region methods were developed, and we'll see how we can extend some of those approaches to handle constraints. Okay, so in the rest of the talk, I'll first describe sequential quadratic programming. So this is maybe something that we don't necessarily teach in an introductory statistical computing classes, but this is going to be a workhorse for the methods that we are developing. Then I'll talk about stochastic SQP with line search and also stochastic SQP with a trust region method. And then if there is time, I'll briefly discuss some of the extensions to inequality constraints and randomized algorithms. Okay, so what is a sequential quadratic programming? It's a method, like it's a state-of-the-art method for solving the problems of the following form, where we have a smooth objective f of x subject to some smooth constraints c of x is equal to 0. And so here we are in the deterministic setting, and I'll later show you how we can how we'll move to stochastic setting. So just for notation purposes, this is a Lagrangian. So it's a f of x plus Lagrangian multiplier lambda times c of x. And the SQP, you can think of it, it's an algorithm that we use to find a KKT point of this system. Okay, so you can just think of like one way to view SQP is it's a method that finds x star lambda star that satisfies this equation. So finds the point where the gradient of the Lagrangian is equal to 0. An alternative way to think about SQP is that it's a method that tries to minimize in each iteration the objective of the following form. So you have a quadratic approximation of your Lagrangian, just like in gradient descent, you have a quadratic approximation to your function. Here you have a quadratic approximation to your Lagrangian, and then you have a linearized version of your constraints. So irrespective of which view you take of what SQP does, you end up at the following kind of a Newton system. So in each iteration, the way SQP tries to find the descent direction is by solving the following system of equations. So it tries to find delta x, delta lambda, that is a solution to this system of linear equations. Delta x is going to be the search direction. And in this notation, BK is some approximation of the Lagrangian Hessian. For example, it could be an identity matrix or some other modification of the Hessian. Okay, so now the difference with, let's say, Newton's method for unconstrained problems is that we cannot use the objective function to determine how we are progressing in the algorithm. So in unconstrained problems, we can use the objective function together with the search direction to decide how much should we move in the direction of the search. Here, we cannot just use the objective value because that does not take into account the constraints. So I could improve my objective value, but the constraints might not be satisfied. So I need to have some way of measuring progress that both takes into account the objective function and the constraints. And so one such way is to use a differentiable exact augmented Lagrangian, which combines the Lagrangian and then augments it with the term that includes the constraints and the term that includes the feasibility. Sorry, the optimality of the point. Okay, so we want to find a point that's both feasible and a stationary point of the Lagrangian, and we will use this as a way to track progress to a stationary point. In this case, I will not discuss this in detail, but nu is sort of a free parameter. We don't need to adaptively choose it. We can set it, say, as 1. But parameter mu is something that, in addition to length of the step size, needs to be chosen in each iteration of the algorithm. So we will design an algorithm that optimizes for mu, that finds a mu, as well as decides how much to move in the direction of delta x. So our algorithm is going to be proceeding in the following way. So we solve the linear system on the previous slide, and our next iterate is going to be of the following form. Now, how do we choose alpha k? Well, we'll choose alpha k so that the following Armijo condition is satisfied. So here, this notation where we put k plus 1 and k in the superscript just indicates that our augmented Lagrangian is evaluated at iterate xk plus 1 or iterate xk. Okay, so I want to find alpha for which this holds. So now one algorithm that we're going to be kind of using as a blueprint for development of our stochastic procedure later was developed in this paper by Lucidi in 1990. And I'll show you, in next how this algorithm works in the stochastic setting. Okay, but this is roughly what the idea is. Now, in the stochastic setting, just remember, we don't have access to function f of x. We only have estimate of this function. We'll estimate it based on the samples obtained based on the samples that we have. So the adaptive SQP kind of algorithm, which we develop, which we expand from Lucidi, works as follows. So we are going to consider a sequence of iterations. There are some input parameters. So nu, remember, is a parameter for the augmented Lagrangian. It doesn't really matter what we choose. Think of this as 1. Mu0 is the initial penalty parameter. And the rho and delta are related to the algorithm, as we'll see later. Okay, so how do we proceed? So we solve a linear system as follows. That is going to tell us how to choose which direction to move. So this is a augmented linear system where we try to identify delta x and delta lambda. Then we find penalty parameter mu that is large enough. And this condition here essentially ensures that we will have a decrease in the merit function. So our augmented Lagrangian, it's a merit function that we use to track progress of the algorithm. And mu needs to be chosen large enough so that the merit function decreases. So then this is an adaptive way to set the penalty parameter mu for the merit function to ensure the decrease of it in the in each iteration. So this is a for loop that adaptively allows us to increase penalty parameter mu as well as this accuracy delta. And then once we select the penalty parameter mu, we choose the step size alpha by using the Armijo condition. So we choose alpha large enough so that this is satisfied, and we update the iterate in the following way. Okay, so that's the blueprint from Lucidi that we're going to develop for the stochastic setting. Okay, now in the stochastic setting, there are some challenges that don't exist in the deterministic setting. So here are the challenges. The first challenge is that this function the Lagrangian is not deterministic anymore. It's a random quantity. So that means that even if I choose the step size alpha in such a way that this is decreased in one iteration, it does not mean that across many iterations these decreases are going to aggregate. Okay, so these iterations may not accumulate over iterations. Another issue is that the bad estimate of either the Lagrangian value or its gradient may not, if I incorrectly estimate these, my step size might become arbitrarily small. So that's another issue. And even if this Armijo condition holds, like the objective in expectation may increase. So the way we are going to handle these difficulties is that we are going to try to estimate the model accurately enough. So we'll allow for some probability of making a mistake, but if my model is accurately estimated, then the line search step is going to ensure validity of the selected random step size. Just kind of like a reminder of the notation, if you have a quantity that has a bar above it, that indicates that it's a random quantity. Okay, so there are some additional challenges with constraints. The search direction is going to be a descent direction of this augmented Lagrangian only if the penalty parameter is large enough. And so in stochastic setting, the penalty parameter mu is going to have some kind of random walk, and eventually it's going to stabilize. And so the value at which this random walk is going to stabilize might be above the threshold needed to ensure that this search direction is descent direction, or it may be below. So in some cases, we might not ensure the decrease of the augmented Lagrangian. So that's one issue. And another issue is that not every stationary point of this augmented Lagrangian is a KKT point. So in particular, we see that the following relationship holds between the gradient of the augmented Lagrangian and the gradient of the Lagrangian. So if this matrix here is not of full rank, then there might be some stationary points of the augmented Lagrangians that are not stationary points of this Lagrangian, of the non-augmented Lagrangian. And so that points out that mu needs to be large enough so that this matrix here is of full rank. So the way we are going to ensure this is we'll have a while loop that's adaptively going to increase the penalty parameter mu until we have the following constraint satisfied. So if the gradient of augmented Lagrangian upper bounds the norm of the constraint, that indicates that we are converging to a feasible stationary point of the Lagrangian, and this will hold. Okay, so that's kind of the idea. So at glance, I'm going to show you the 4 steps that our algorithm goes through. So in each iteration, we follow 4 steps. So we have some iteration where we have kind of current estimate of the primal variable, current estimate of the dual variable, as well as the current the step size, and as well as the current accuracy of the model. So then we compute an estimate of the gradient and of the Hessian. Now, in order for these to be good enough, we require the sample size to be large enough so that this event holds with some pre-specified probability. So this p grad, it's an input parameter to the algorithm, but as I'll show you later in simulations, it's not necessarily crucial input. Let's think of this, that this event holds with probability 90%. Okay, so there's 10% in each iteration that this is not a good estimator of the gradient. But this condition essentially tells you that with some prefixed probability, not probability going to 1, we have a good estimator of the gradient. The details are not very important, and what I want to emphasize is that we can choose the size of the batch in a problem-specific way to ensure that this event holds with pre-specified probability. Next, we solve the linear system to figure out what is the direction of the search, and then we update the penalty parameter. So this is something that we already had in the deterministic setting. This term is unique to our stochastic setting. So we require that the gradient of the augmented Lagrangian upper bounds the norm of the constraint, and this is somehow needed for the proof of the convergence later on. Okay, otherwise we have the issue that we may converge to a infeasible stationary point. Then the third step is, once we figure out the search direction, we need to figure out how much to move in that direction of the search. And so here we generate a new batch of samples that we use to estimate the objective value and the gradient of the objective that allow us to estimate the merit function, the augmented Lagrangian. And so again, we have an event that will hold with, let's say, 90% probability. And this event is such that augmented Lagrangian and its gradient are accurately estimated. So this event just tells you that the estimator of the merit function and its gradient are accurate enough. Okay, so that's it. And then once we have this, we can proceed with our Armijo condition. Okay, if we do not observe, so now the Armijo condition, in addition to Armijo condition, we need to check whether the decrease is sufficient or not. So in particular, for each iteration, we are also going to investigate whether we have sufficiently decreased the merit function. And if we observe a sufficient decrease in merit function, then we are going to relax the accuracy condition. So epsilon essentially controls how much samples I need in each iteration to accurately estimate either the to estimate the merit function. And if we observe the sufficient decrease, I'll in next iteration require fewer samples. I'll need a less accurate estimator. And otherwise, if I don't observe sufficient amount of decrease, I will make that condition more stringent so that the next iteration we require more samples to get more accurate estimator of the merit function. Okay, so that's the algorithm. Now let me briefly tell you when this algorithm works. So we make following assumptions which are more or less standard in the literature on optimization with constraints. So we assume that our iterates and kind of the proposal points all lie in some convex compact set. We assume that functions f and c are 3 times continuously differentiable. We don't need the function, we don't need to compute the third order derivative of these functions, but we need this to kind of prove closeness of the Hessian. We will assume that Jacobian has a full rank over the space, and we will assume that our Hessian approximation is full rank over the null space of Jacobian. And then this last part is sort of needed for analysis so that we can generate infinitely many iterations. Okay, so now some assumptions that are maybe less standard. We require that the function is essentially, for any realization, it's bounded. This is not stringent in the context of finite sum minimization, because anyhow, things are bounded. But we need these assumptions or some assumptions like this to use Bernstein's inequality when we are controlling for the size of the batch. Okay, so we can relax these conditions by allowing some tail conditions on the gradient and function value estimations, as long as we could use Bernstein's inequality down the road to determine the batch size. Okay, so how do we prove convergence? We will use a potential function to keep track of the progress of the algorithm. So this potential function is kind of carefully crafted to combine the augmented Lagrangian term, the accuracy of the estimation of the augmented Lagrangian in each iteration, as well as the feasibility of a point. And what we'll do is we'll study the behavior of this potential function after some number of burning iterations. So k bar is a random quantity, but after this quantity, the penalty parameter stabilizes. So we can show that almost surely in every run of the algorithm, there exists a finite k bar such that this potential function behaves nicely after these k bar iterations. And so the way essentially the algorithm proceeds is that the analysis proceeds is that when we estimate the gradient of the function well, and when we estimate the Lagrangian function well, in that case, the potential function decreases. Okay, so somehow on a good event, we have a sufficient decrease in this potential function. Now, on a bad event, for example, when we do not estimate the gradient of the function correctly, then the potential may increase, but an increase in the potential is not large. And finally, if I do not estimate correctly the augmented Lagrangian, then again, my potential function can increase, but not by much. So then putting these pieces together, we have that essentially we can show the following one-step error recursion, which says that in expectation, conditional on the filtration that we're conditioning on all of the information up until iteration k, the expectation of this will decrease of the potential function. And this then subsequently allows us to show that our iterates converge almost surely to a stationary point of the original of this Lagrangian, and also there is a limit bound on the iterates. So this result is very similar to what we have in non-adaptive stochastic SQP. We essentially have under this condition, this implies that alpha k decays to 0. So this we would require to converge to a almost sure to a stationary point of the objective. Now, with adaptive algorithm, a subsequence of this sequence is lower bounded away from 0. But we need somehow a more stringent stochastic setup. And it's also worth comparing to deterministic SQP, where alpha k is lower bounded away from 0 for large values of k. And so we don't have this result, but there is a subsequence which is always bounded away from 0. And what we'll see is that when we look at some empirical results, we will see that the step size kind of increases, is large in every now and then, which speeds up the convergence of the algorithm. Okay, so how did we test this algorithm? We look at essentially a number of optimization problems from this QTest test set. So this is a benchmark collection of problems with constraints, and we are looking at subset of these problems. We are going to look at problems where there is no non-constant objective. We are going to look at problems where the number of dimensions is less than 1,000. We are going to look at problems where the Jacobian is of full rank during the iteration of the algorithm. And so in the end, we we have 47 problems from this test set that we are going to apply the algorithms to. We are going to benchmark 4 algorithms. So first algorithm is a competing procedure from Albert Barajas and Quarters, where they have a fully stochastic line search method. So in each iteration, they're generating one sample and then making an update. In comparison, we are looking at the batch of samples to approximate the Lagrangian and then making our update. We are also going to look at the non-adaptive version of the stochastic SQP. So this is something where I pre-specify the step size sequence alpha, irrespective of the problem, and look at how that behaves. And we will then compare with adaptive version and illustrate the benefits of adaptivity. And then finally, this is something I did not discuss with you, but a very typical merit function that people use in constraint optimization is L1 penalized Lagrangian. So you have like objective function plus L1 penalty on the constraints. This has some issues in the deterministic setting. That's why we are using the adaptive. That's why we are using augmented differentiable Lagrangian. But it's something that we can compare with in experiments. Okay, so our empirical setup is that we are going to look at this QTest test set, and we'll initialize primal dual variable as they are initialized by the QTest package. This collection of problems are, these are deterministic problems. So we need to generate a stochastic oracle based on that. So the way we're going to generate a stochastic oracle is that we're going to add Gaussian noise to evaluation of the function gradient or Hessian, and we will change how much noise we add. Throughout the experiments for all algorithms, BK, which is the approximation to the Hessian, is going to be identity. And our stopping criteria is going to be such that we stop when we don't make much progress, or we reach a stationary point, or we exceed our budget of 10,000, our budget of 100,000 samples. And for each one of these problems, we'll generate 5 independent runs. So first, I want to illustrate to you what the convergence behavior is. So when the noise is small, then it seems like all the algorithms work just fine. They converge to the same, the KKT residuals are similar. Now, when the noise increases, what one might observe is that these alternative approaches do not work as well. And in particular, our non-adaptive SQP does not converge. It's essentially, one needs to carefully choose the step size sequence so that one ensures the convergence. So here, I also want to emphasize that beta K is the procedure that Barajas procedure uses to kind of adapt the step size. When we have similar behavior or similar observation when the step size sequence decreases, it seems that our method is more robust to the noise level in the problem. Now, in terms of robustness to the tuning parameter, like we have some tuning parameters to choose. In particular, these parameters C grad and CF determine how many samples should we use in the batch. And what we can see is that the algorithm is not too sensitive to the different choices of the parameters C grad and CF. Also, one can ask a question, like if I have a fixed budget of, let's say, 10,000 samples, how will my algorithm converge? And in this case, what we observe is that again, the benefits to our algorithm, especially when we are in the noisy setting. Okay, so when the problem is far from deterministic, there's quite a lot of benefits to using the adaptive algorithm for optimizing these problems with constraints. Okay, and finally, what I want to kind of illustrate is I can plot for these problems. So I've chosen, let's say, 10 convergent subproblems from the QTest test set, and I'm looking at how does the step size evolve as a process through different iterations. And you can see that for the adaptive SQP, every now and then the step size increases away from 0, and sometimes it's even bigger than 1. And this is allowing the algorithm to make faster progress than if you have a step size sequence where that decays to 0. Okay. Okay, so this is what I was planning for the kind of first part of the talk. Now, I realize I don't really have much time to go over this second method, which, so I'll just briefly mention it, something that we are currently working on. In one way to achieve adaptivity in deterministic setting is to use line search. Another way to obtain adaptivity is to use trust region method. So what is the difference? So this is a figure that I've shamelessly taken from book from Jorge Nocidal and Steve Wright that illustrates the difference between the line search method and the trust region method. So in both settings, what you want is you want to optimize this function where the counters are given by the full line. And you have a current iterate, like this point here is the current iterate. So in both cases, you come up with the model of what you believe the function is. So you have a quadratic model. The counters of the model MK are given by the dashed lines. Okay, and so the line search method, what it tries to do is it tries to find a direction, this one, that minimizes the model. So the direction of this descent is given with respect to the model. And then you're using a line search procedure. Once you identify the search direction, you're deciding like how much should I move in this direction to minimize the model. The trust region, rather than having two steps, looking for the search direction and then looking how much to move in the search direction, it says, well, I'm gonna have my model MK with the dashed lines, but I'm going to put this kind of like circle, trust region radius, that tells me in what region this model is a good approximation to the unknown function f. And then by solving this optimization problem here, we're going to simultaneously decide how much to move and in what direction to move. Okay, so it's like a one-step procedure that decides where to move and by how much, rather than having a two-step procedure as in line search. And so this has some benefits. It's kind of experimentally, it works better in many problems. It also allows us to use a negative definite Hessian matrix. We don't need to modify it like in line search to be positive definite. And it seems to be more robust to ill conditioning. And so this is what kind of our procedure, kind of our first stab at this type of direction was in a paper by Yucheng Tang and Sen that was recently accepted to SAM Journal on Optimization, where we develop a fully stochastic method for solving problems with equality constraints. So given the time, I won't really have, I don't have time to go into the details, but you can find this in the archive paper here, and soon the paper will also be published. Okay, so I'm gonna just skim through the details of the algorithm. And maybe I'll just mention that for this type of procedure, we can prove similar results as for stochastic gradient descent. So depending on how we choose to model the step size, we will either converge to a ball, the KKT residuals are either going to converge to a ball of radius that modifies the trust region radius, or we are going to converge almost surely to a stationary point of the problem. So we get analogous results to stochastic gradient descent. Okay, so we have some results, and I want to just briefly kind of talk about two extensions to advertise some other work we've done. So one paper we wrote with Sen that was also accepted by, that was published in Mathematical Programming, is how to handle inequality constraints. And so here we develop an active set algorithm based on the SQP, where in each iteration we solve a subproblem that is an equality constraint quadratic programming. And we need to modify the algorithm that we discussed so far. So we need to consider additional search directions to prove convergence of this algorithm. So the details are reported here. And a paper that got published in ICML 2023 with Ilge Hong, we investigated a work where we are using randomization to solve the inner Newton system. So essentially, one computationally costly part of SQP is solving a linear system. Just like in the Newton's method for unconstrained problems, finding the search direction is computationally expensive. So here we are investigating how can we use a stochastic randomized solvers to solve this equality constraint, to design an algorithm that will provably converge to a stationary point of the constraint problem. And so this is a work in a deterministic setting. Okay, so in conclusion, what I've told you about today is a class of algorithms for solving stochastic problems with equality constraints. I only had time to tell you about the design of a line search method in a random model setting, meaning in a setting where you can collect a batch of samples to approximate the function. I did not have time to tell you about the trust region method in details. For both of these methods, we were able to prove almost sure global convergence, and we have some preliminary results, preliminary numerical results that illustrate the effectiveness of these methods. But I think applying these methods in some interesting problems like physically informed machine learning systems would be something of interest. And that's something that we are pursuing at the moment. As a statistics audience, one thing that I'm personally quite interested about is what kind of statistical properties can we prove about the iterates coming out of these problems. So for example, for stochastic gradient descent, we know it has a normal limit with certain variance covariance matrix, and we can estimate that variance covariance matrix sufficiently even when we are doing this in an online setting. So the question is, can we develop similar algorithms for constraint optimization? That's very interesting. Something that is also of interest is, so far I've only told you how to find first order stationary points, but we're interested in minimization so that we can design algorithms that converge to a local minima of these problems is something that is worthwhile investigating. And then some problems that I'm personally interested in is whether we can apply these techniques to design safe reinforcement learning algorithms, or how to develop distributed methods when we have constraints based on the methods that we are discussing here, is all of kind of interest. So there are a lot of, I think, open problems, as well as kind of directions to making these algorithms more benefit from more eyes and more brains on how to solve them. So with that, thank you. Here are some works on the papers that we have completed so far, where you can find additional details. So thank you.